Now, if you go back to set theory, we use the term disjoint for the same thing. Uh, disjoint sets would be two sets that do not intersect. In other words, if the intersection of two sets is empty, then we say that two sets are disjoint. The same term can be applied here, or another word for the same thing is mutually exclusive events. So let me define the mutually exclusive event in a slightly different way. It is, in fact, same as disjoint sets, and you will see that in a minute. So mutually exclusive events are two events that cannot occur at the same time. Two events that cannot occur at the same time. Okay, so let's look at an example. Toss a coin and a die at the same time. The event F is defined as even number shows on the die. Event G is defined as odd number shows on the die. Then these two events cannot occur at the same time. They are mutually exclusive. So if you take the event F, and if you actually write down the event F, I'm trying to write down the event on the board. Event F, which is even number shows up on the die. But this is a die and a coin. So that means H2, H4, H6, T2, T4, T6. These are the elements that make up the event F. If one of these is the outcome, then you have an even number on the die. G is odd number on the die. So that will be H1, H3, H5, T1, T3, T5. All right, so the fact that they cannot occur at the same time is clear, but notice that if you remember from earlier discussion, the event of both happening is same as intersection. So F intersection G has to be the event of both happening. So if you look at the F intersection G, there's nothing common. It's empty. So that's when they both cannot occur at the same time. There's nothing common. If there is anything common, if there is a T2 that's also here, then when the T2 is the outcome, both events happen. But there's nothing common to both. So there's no way both of them can happen. So in other words, what I'm trying to say is, even though definition of mutual events, mutually exclusive events says these are events that cannot occur at the same time, that's equivalent to saying the intersection of them will be empty. So two events are mutually exclusive if and only if the intersection is empty. If the intersection is empty, then the probability of the intersection is equal to count of the event intersection over count of the sample space. The count of the intersection is 0. So 0 over whatever the sample space count is, the whole thing is 0. So therefore, the probability will be 0. So there is an equivalent statement here. Two events, that's what I have in the box here. Two events E and F are mutually exclusive if and only if E intersection F is empty, or equivalently, probability of E intersection F is 0. So you can check on a Venn diagram, you can check to see if they do not intersect. If they do not intersect, then they are mutually exclusive. That's if you have the Venn diagram. Otherwise, if you have the description of the set, then you can figure out what the intersection E intersection F is and see if it is empty. Or if you already have numbers, you can figure out the probability, then the probability should be 0 for them to be mutually exclusive. So using whatever the information you have, there are 3 ways to do it. Find out whether they intersect on the Venn diagram, or find out whether the intersection F is empty, or the probability is 0. Okay, so let's look at another example. 2 wheels are rolled, and so the wheels on the right side rolled, and the numbers show up. Event E is defined as the numbers show up on the wheels should add up to 8 or less Event F is defined as second wheel shows 507. Okay, then find probability of E and F. That means we have to write E and F. We have to write out E and F. So can somebody tell me what would be E, the elements of E? Uh,
1, 2, 3, 4.
1, 4 is not an element of this element of the sample space. We are rolling these two wheels.
1, 5.
1, 5, yes. And
1, 6, 1, 7, 1, 8.
1, 7. They have to add up to 8 or less. So therefore, we cannot have anything more than 7, right? So 1, 6, 1, 7.
Isn't
Two,
anything
6.
more than 8?
Numbers that show up on the wheels add up to 8 or less. No, we are not finished. We have written 3 of them.
2, 6.
Yeah, there's more. 2, 6.
3, 5.
That's right. 2, 6, 3, 5. And anything else?
1. No.
That's it, right?
Yeah.
Okay.
And
So
2, 5.
1, what was that? I'm sorry?
2, 5.
2, 5. Did we miss 2, 5? Yeah, we
Mm.
you're right. Okay, comma 2, 5. Okay, I think we have everything now. So let's close that and let's write down the F. F says we should have second wheel showing 507. That means first wheel can be anything. So therefore, 1, 5, 2, 5, 3, 5, 4, 5. And then 1, 7.
2, 7, 3.
Right. 2, 7, 3, 7, 4, 7. Okay, and that's it. All right, so the probability of E is probability of E equal to, there are 6 elements in E, so 6 divided by, how many elements will be in the sample space?
16.
16, very good. So therefore 6 over 16. I'll leave it at that without reducing. And then probability of F would be, there are 8 elements there, so 8 over 16. Okay, so going on to the second question, are E and F mutually exclusive? Well, you can just look at the intersection. Is there anything common to E and F?
Wouldn't the probability of F be 1/2?
I'm sorry, one more time. What's that?
Wouldn't the probability of F be 1/2? Because
Yeah,
it's
yeah,
split.
it'll reduce to 1 over 2. That's right.
Yeah.
I didn't do the reducing part. Yeah, that's right.
Would it be okay if that was to come out as a decimal of 0.5?
Yeah, 0.5 is right, but
Because I know there's some that asks for like the certain places. So what if one problem has, since PE is 0.375 and PF is 0.5?
yeah, they're correct numbers, but whatever the web design problem asks for, you had to enter that. Sometimes they ask for the fraction, sometimes they want the number, and you have 3 chances to figure out exactly what they wanted.
If they were to ask for like a 3 decimal place, since the first one had a 3 decimal place, would I just put 0.500 for the second one to submit the answer, or 0.5
Right.
would be okay?
0.5 would be still okay.
Okay.
The zeros behind it are automatically assumed,
Okay.
so you don't have to enter them.
All right. Thank you.
You're welcome. So yeah, if you reduce, then it's 3 over 8 and 1/2. To figure out E and F, whether E and F are mutually exclusive, I'm going to find E intersection F first. So find E intersection F. That would be, what are the elements we have in the intersection? 1, 5.
1, 5,
2, 5,
3,
3,
5.
1, 7.
Okay, 1, 5, 1, 5. We have 2, 5. Yes, 2, 5. 1, 7. Anything else?
And 3, 5.
3, 5. Yes, 3, 5 too. So we have 3, 5, and I think that's it. So since we have all these in E intersection F, they're not mutually exclusive, right? It's non-empty. So the answer to the question is no, they're not mutually exclusive. So then it says, how do they occur at the same time? Well, if the outcome is one of these, the actual outcome is only one pair of numbers, right? If that outcome, the pair of number is one of these, then both events happen. So, I mean, if it is one of those, then the numbers show up, numbers add up to 8 or less is true. And also the second wheel shows 5 or 7 is also true. In other words, both events happen if the element is one of those in the intersection. So that's the answer you provide.
So how would we answer the how do they occur? Just saying that they both occur at the same time?
No, if they say, how do they occur at the same time? You say, if the actual outcome is 1, 5, or 2, 5, or 2, 1, 7, or 3, 5, if it is one of those, then both events occur.
Okay.
All right, that's how you say it. So find the event E intersection F, we already found it. And then compute probability of E intersection F, okay. That's, what is it?
4
4
over
over
16.
Right, 4 over 16. 4 over 16 equal to 1 over 4. And then it says find F bar, complement of F. So that's everything that's not in F. That would be 1, 2, 1, 3, 1, 4. And 2, 3, 2, 4. Yes, 2, 3.
Wouldn't it be 1, 6, 2, 6, 3, 6, 4,
Oh.
6, and then 1, 8, 2,
Yeah,
8?
I'm sorry. I'm all wrong here. Yes, we have 1, 5, 1, 6, 1, 7. So 1, 8 is going to be in the complement. 1, 8. And then we have 1, 2, 5, 2, 6. We have 2, 5. So 2, 6, 2, 7, 2, 8 are in the complement.
And 1, 6, 2.
8. Do we have 1, 6? Yes, 1, 6. I keep looking at E, that's why I'm missing it. Okay, 1, 6. 2, 5. 2, 5 is not in the complement. No.
You
Would
you
it have been
enter
easier?
I'm sorry. Yeah, I'm still finding E complement. Oh, sorry. I could keep losing where I am supposed to be. All right, I'm here. All right.
Wouldn't F complement be what's inside of E, but not in F? Because we didn't find the sample space.
The sample space is clear. It's, you know, the pairs with one, if you start with one in the first wheel, then 1, 5, 1, 6, 1, 7, 1, 8, and then 2 in the first wheel will combine with all the numbers 2, 5, 2, 5, 2, 2, 7, 2, 8, and so on. So we don't have to write it down. We can tell what it is. So, so what we need to do is to find F complement. We just have to find all the elements in the sample space that are not in F. And to figure out, I don't have to have the sample space, but it has nothing to do with E. This is F complement. So only look at F and find out what's outside of F, what is not in F. So 1, 8 is an element of sample space that's not in F. And 1, 5, 2, 5, 3, I mean, 1, 5 is in this, 1, 5, 1, 7 are here in F. So everything other than 1, 5, 1, 7 would be 1, 8 and 1, 6. 1, 6. Yeah, we missed 1, 6. Okay.
And 2, 7 is in F. So
2, 7 is there, right? So I misread it. 2, 7 is there. So that's not in the complement. So 2, 5, and 2, 7 are here. So everything else will be in the complement. That would be 2,
3, 6.
2, 6, and 2, 8. 2, 8 is
Excuse
already.
me, Professor. How did we get 1, 8?
You know that 1, 8 is part of the sample space, right? And 1, 8 is not here in F.
I think it's a little complicated for me because I didn't write out the sample space.
Okay, I can write out the sample space. Sample space will have 1, 5, 1, 6, 1, 7, 1, 8, right? Okay. 1, 5, 1, 6, 1, 7, 1, 8. And then 2, 5, 2, 6, 2, 7, 2, 8. Same thing with the 3. 3, 5, 3, 6, 3, 7, 3, 8, 4, 5, 4, 6, 4, 7, 4, 8. All right, so that's all we have in the sample space. So basically you need to find everything that's not in F. So 1, 8, say 1, 5 and 1, 7 are in the EF. So therefore 1, 8 and 1, 4. No, 1, 4. I'm going to start there. So 1, 8, 1, 5, 1. What about 1, 6? Yep, I have. That's why I have 1, 8 and 1, 6 in the F bar. And then with the 2, 5, 2, 7 are F in F. So the remaining ones are 2, 6, and 2, 8. Going to 3, 3, 5, and 3, 7 are here in the F. So everything else will be in this complement. That will be 3, 6, and 3, 8.
What about 4, 6, and 4, 8?
Yeah, that will be the next one. 3, 6, 3, 8, and then 4, 6, 4, 8. I believe that's it. Okay, so the probability is just the count divided by the count of the sample space. The count is 3 plus 6, 8. 8 over 16 is the probability. And okay, probability of F and probability of F bar have to add up to 1, right? It asks you to verify that. All right, so you know how to do that. Let's go to example 6. The event E or F occurs. Now we discussed this earlier, but let's do it in a formal way again, using some examples. Event E or F occurring. So I'm going to use this example of tossing a die, 6-face die is rolled. Event E is defined as odd number shows. Event F is defined as less than 4 shows. So event E is 135. Event F is 123. Less than 4 would be 123. Now, event E will occur if 1, 3, or 5 is the outcome. Now we are tossing the die once, and if 1, 3, or 5 is the outcome, then event E occurs. If 1, 2, or 3 is the outcome, then event F occurs. So if I say I need event E or F occurring, that means any element here and any element here, if you look at the combination, and if any one of those is the outcome, then E or F occurs. So, so if I need to have E or F occurring, then I just need to find all of these, find the event of all those things together. That's 1, 2, 3, 5. So as you can see, if outcome is 1 or a 2 or a 3 or a 5, then E occurs because it's here, and F occurs. I mean, or I'm sorry, if it is 1, 2, 3, or 5, then either a E or F occurs. So for example, let's look at or both. So for example, if the outcome is 1, then E has occurred and F has occurred. If the outcome is 2, then F has occurred. E hasn't. So we only want E or F to occur. So that means one of these needs to be the outcome. As you can see, the same as the union. In other words, for one event or the other event to occur is same as the union should occur. So the event of E or F occurring is same as the event E or F occurring is same as E union F occurring. So whenever they ask for the probability of E or F, you need to find the probability of the union. So this in this Venn diagram, I have shaded the two circles together to represent the event E or F occurring, or E union F occurring. All right, so let's look at some reason this is. All right, the picture is messed up for some reason, but you can see what they are. The section, the left section of E has 0.3, the intersection part has 0.1, and the probability outside is 0.2, and we need to find the probability of E union F. So that means I had to figure out the remaining section, the unknown section. Can somebody tell me what the unknown section is equal to? The right side of F?
0.4.
0.4, that's right. So that's 0.4 right here. So that means what is the probability for the union?
0.8.
0.8 is correct. Just add up those three numbers, 0.3, 0.1, and 0.4. That's the probability of the union. Okay, so if they give you the counts, then you have to work with the counts on your Venn diagram. So here in this problem, they give you the counts. So let me go to the board. This is.
Hey, Professor.
Yeah.
How did you get 0.4 for the last exercise?
Okay, the 0.3 is the entire Venn diagram, entire sample space probability probability of the sample space is 1, right? So all these numbers have to add up to 1. So that's why we added 0.3 and 0.1 and 0.2. That was 0.6. So to add up to 1, this has to be 0.4.
Oh, I see.
Okay. Basically, I'm subtracting the 0.6 from 1. That gives you 0.4. Okay, exercise 13 gives you numbers. I'm going to go over this very quickly because this is not new. We have done this many times. But only thing we are doing differently here is finding probability instead of counts. But earlier in the set theory, we did these problems for counting, just counting different sets. Now it's probability. Other than that, it's the same thing. Okay, so in the Venn diagram, we have 20 children in the daycare, so the count of sample space is 20. 11 have black hair. 11 have black hair, and 7 have brown eyes. R for brown, 7. 5 have both, so 5 here. A child is randomly selected. What is the probability for all these? All right, so we need to figure out these sections. So this left side of B is
6.
6, and right side of R is
2.
2, and we have to now calculate the outside.
Seven.
7 outside. Okay, so with that, we are ready for the answers. First question is, what is the probability that the child has black hair? Anybody? Answer the first question.
11 over
6.
20.
11 over 20 is right. If anybody is not following, ask the question. Part B.
Why would it be 11 over 20? Wouldn't it be 6 over 20?
No, 6 is on the left side of B, 5 on the right side of B. B has 11. See that?
Yeah, but it's only asking that has black hair.
Yeah, these 5 have black hair, don't they?
Okay. Wouldn't that be including with the brown eyes though, the 5?
Yeah, but they do have black hair. The question is, what is the probability that the child has black hair? All these 11 children have black hair.
Okay.
All right. It doesn't say what is the probability the child has black hair but not brown eyes, right? Only then it'll be 6.
Okay.
If I say what is the probability the child has black hair but not brown eyes, then it'll be 6 over 20. Okay. All right. Part B. Anybody?
7 out of 20.
7 over 20. And part C,
5 out of 20.
that's, wait, where are we? Part C, black hair and brown eyes, right, 5 over 20. And part D is?
7 over 20.
13 over 20.
I think you're reading the wrong question. D is black hair or brown eyes.
Yeah, it's 13 over 20.
I read the wrong question, sorry.
You were reading the wrong question. So 13 is correct. 13 over 20 is right. And part E is, anybody?
6 over 20.
Right, that's what 6 over 20 would be. Part F is?
7 over 20.
7 over 20. The children that are outside the 2 circle will have neither. That's 7. So 7 over 20 is right. All right, so moving on to exercise 14. Okay, so we are going back to the additive rule. We learned this additive rule for set theory, count of sets. Looking at this example that we just did, there are 6 on the left side of B, 5 in the middle, 2 on the right. So the union has 13, 6 plus 5 plus 2, right? But if you add the number of elements in B, that's 11. Number of elements in R is 7. 11 plus 7 is 18. Why is 11 plus 7 not equal to the count of the union? Because these 5 are getting added twice when you add the 11 and 7. The 11 includes the 5, 7 includes the 5. So that's why we said count of A union B is not equal to count of A plus count of B. the count of A plus count of B includes the intersection twice. So therefore, you had to subtract the intersection once to get the correct count. So we learned this formula when we did set theory, counting of sets. Count of A union B equal to count of A plus count of B minus count of A intersection B. The same rule is going to apply to probability with the probability numbers. So I'm using this picture for the probability. Exercise 14 has a Venn diagram on the right side. So I'm looking at the Venn diagram here. The left side of E has 0.3, the right side of F has 0.4, the center, the intersection has 0.1. And as you can see, the probability of the union is 0.3 plus 0.1 plus 0.4, which is 0.8. But if you add probability of E and F, I'm writing on the board, probability of E plus probability of F is in fact the probability of E is 0.4, right? 0.4, and probability of F is 0.5. Probability of F is everything in the F, that's 0.5. 0.5, and those numbers add up to 0.9. That's not equal to probability of the union. Why? Because the intersection is being counted twice in those numbers. So therefore, if you take probability of E plus probability of F, that's 0.9. If you subtract the intersection once, E intersection F, probability of the intersection once, then you will get the correct probability for the union. So it's the same thing that we learned in set theory that applies here. Probability of E union F. All right. So here's the so I'm basically trying to prove that formula using the counting techniques. Let me show you how that works. But you can see from the Venn diagram why this is true. But algebraically, I can prove that. So I'm going to show you the algebraic proof, even though you don't really need it. But if you understand it, and just understand the algebraic proof, you know, you will understand better. You will understand the whole idea better. The probability of E union F, I'm writing on the board now. Probability of E union F is defined to be count of E union F divided by count of sample space, right? But the count of E union F in the numerator is equal to E and F are sets. So applying the union rule for set theory, the numerator becomes count of E plus count of F minus count of E intersection F. Applying the union rule you learned for set theory and dividing by count of S. Now, there are, you know that 5 plus 7 over 9 is same as 5 over 9 plus 7 over 9, right? The basic arithmetic, fractional arithmetic idea. So I can split expression like this into 2. So I'm going to do that for all 3 of the expressions in the numerator. I get count of E over count of S plus count of F over count of S minus count of E intersection F over count of S. And this is what probability of E is. Probability of E, probability of F minus probability of E intersection F. So basically I proved algebraically that the counting rule that we learned for set theory applies to probability as well. So going back to the worksheet, this rule is the point. We just learned that probability of E union F equal to probability of E plus probability of F minus probability of E intersection F, and that applies to any 2 events. Now, if those 2 events are mutually exclusive, if E and F are mutually exclusive, then we know that the intersection would be empty and the probability of the intersection will be 0. And that, in that case, this intersection part will disappear. That's 0. So therefore, for mutually exclusive events, the probability of the union equal to probability of E plus probability of F. So in other words, if they don't have anything in the intersection, then E probability of the union F can be found by adding the probability of both of them. All right, so let's do some exercises. Now all this is very similar to what we did in the set theory. You know, it's all the same thing all over again, but this time using doing it for probability instead of count. So probability of E is 0.4, probability of F is 0.5, E intersection F is 0.2. So find the union, find the probability of the union. That's what it says. So that's application of the union rule. The union rule we just learned. It's also called additive rule. Additive rule or union rule for probability. We just have to apply that. So let me do that on the board. Probability of E union F equal to probability of E plus probability of F minus probability of E intersection F. And probability of E is given as 0.4 and F is given as 0.5 and E intersection is 0.2. So the whole thing is 0.7. And that's your answer to the question. Number 16 says probability of A is half, A union B is 3/4, A intersection B is given, find probability of B. Again, it's the same rule applying for A union B. Events are now called A and B. And then in this formula, if they give you any 3, you can find the remaining ones. Property of A intersection B. So in this exercise 16, they have given us the union, so 3/4. Probability of A is given as half. B is the unknown, call it X. Minus A intersection B has 1/4. So we need to solve this for X. So 3/4 equal to half minus 1/4 is 1/4 plus X. So X equal to 3/4 minus 1/4 is half. So the probability of B equal to half. So they're straightforward questions. So let's go to problem 17. The events are mutually exclusive. So our formula becomes what?
Professor?
Yeah.
Back on 16, how did you get rid of the half and then bring it back again?
Oh, I subtracted the half minus 1/4. I did that subtraction.
And it gave you 1/4?
That gave you 1/4.
Okay.
All right.
Yeah, I got 0.25.
Yeah, that's it. If you like to work with the decimal number, you can do that.
Okay.
All right. So 17 says E and F are mutually exclusive. That means our formula now becomes probability of E plus probability of F and no intersection. That part is 0. So E union F is 0.7. Probability of F is 0.4. Probability of E is the question, call it X, and solve this for X equal to 0.3. So answer is 0.3. Okay, so that finishes that. Let's, oops. If I do anything, my pictures are getting mixed up. Anyway, we don't know those pictures. We did this before. We did mark things in the Venn diagram. And all right, that's better. We need to mark on the Venn diagram the events of different things, different events. So it says shade the region that represents the event of E not occurring. E does not occur. What would that be? what do I shade in part A?
The part outside E.
Outside of E. Right, everything outside of E, that's right. So the answer to the question A is, here is E. We don't even have to draw the F. We just shade outside of E. This has to, any outcome in this region will mean E hasn't occurred. E doesn't occur. Part B says neither E nor F occurs. So what do I shade?
Outside the both circles.
Outside both circles. That's right. And so let me skip that and go to C. C says E occurs, but not F.
Shade inside of E only.
The left side of,
Without the intersecting part.
right, without the intersecting part. That's right. This would, if this happens, then E occurs, but not F. F occurs, not E. That would be right side of F, right? Going down to section part E. E or F occurs, but not both.
Both circles without the intersecting part.
Right, without the intersecting part. Both should not occur according to this. That means intersection should not be part of it. So this is what it is. If I come
Can you
in
explain A again?
E again, okay.
No, A, the first one. When E does not occur.
Part A,
Yeah.
okay, part A would be E does not occur. So if the outcome is, so going back to this picture, you know, whatever the experiment is, you know, tossing a die or whatever, the outcome is only one thing. And that one outcome, if it is anywhere in E, then E occurs, right? If it is here. All the points here represent E occurring. So if it is anywhere in E, then E occurs. But if it is anywhere outside of E, then E does not occur. E hasn't occurred, right? If it is outside the E. So E does not occur. The event of E not occurring is same as outside of E occurring. The outcome is outside the E. Okay. Let me use an example. Toss a die. So let's say I'm tossing a die, and the event E is all right. Okay, so I'm using an example now. Let's say I'm tossing a die, then the sample space is something going wrong here. Sample space something went wrong in my setup here. So 1 second, I should be back. All right, I got back. Okay, so let's say I'm tossing a die. The outcome is one of the numbers 1, 2, 3, 4, 5, 6, right? So the sample space is 1, 2, 3, 4, 5, 6. And let's say the event is even number false. So that's 2, 4, 6. If any one of these is the outcome, even number false. So now if I say E should not occur, E should not occur, or E does not occur, that's our event. That's same as what? Isn't that same as outcome being 1, 3, or 5? If outcome is 1, 3, or 5, then E doesn't occur, right? The outcome is not even number. Okay, so E not occurring is same as everything else being the outcome. Anything outside of E being outcome. So 1, 3, or 5 is if one of these is the outcome, then E does not occur. And in the sample space, in the Venn diagram, if E is this, then elements of E are here. 2, 4, 6 are all inside. So which elements will make E not to occur? Anything in the outside. That's how it would be in the Venn diagram. All right, I hope you got that. If you didn't, then we'll have to meet at the office hours because these are things we did in the set theory, and I don't need to spend, I cannot spend too much time on that. We can discuss that if you visit my office hours. All right, going over to exercise 19. The E and F are mutually exclusive. That means, look at the Venn diagram. That E and F are mutually exclusive means they should not intersect, right? There's nothing common. So my two circles are away from each other. They have nothing in common in the picture. So now it says probability of E is 0.13, probability of F is 0.21. Find all these other ones. Okay, so let's go to the board. And I'm going to mark the, put it on the Venn diagram. I have two circles, but they are not sharing anything. So the E has 0.13 probability for E, 0.13. Probability of F is 0.21. And first question is, what is the probability of E intersection F? What's the answer?
0.
0. Part B is probability of F complement. What would that be? Probability of F and probability of F complement will add up to 1. So therefore, probability of F complement is 1 minus probability of F, which is 1 minus 0.21. And that's 0.79. Part C is E intersection F complement. Okay, there's nothing difficult here, but you may have to think for a second to figure out the answer. What is the probability of E intersection F complement?
0.66.
No. Think about what is E intersection F.
Oh, I thought you said union. So it will be 1.
1 is right. E intersection F is empty, or probability of E intersection F is 0. So E intersection F complement, E intersection F complement is the entire universal set because E intersection F is empty. So E intersection F complement is universal set. So the probability of E intersection F complement, E intersection F complement is 1 because E intersection F is empty. Part E says, what is the probability of E intersection F complement? That's part of E that's outside of F, right?
0.13.
0.13, right, all of E, because all of E is outside of F. So probability of the E intersection F complement is same as E itself. So probability of E intersection F complement is same as probability of E, which is 0.13.
Did we do letter D?
Letter D, did we skip that? Yeah, you're right, I skipped it. Probability of E intersection F, no, that's what we just did.
No, we skipped the C.
We skipped the C, you're right, we skipped C. And we did the D. Okay, sorry about that. I did the D and skip C. All right, go back to C. Question.
Yeah, I was so confused.
Okay. Okay, which one? You want me to start over?
Yeah, do C again.
All right, part C again. All right, let me erase all this. Part A, E intersection F is empty, and therefore probability of E intersection F is 0. Right, part A is clear. Part B is F complement. F complement would be everything outside of F. That will be probability of F complement is 1 minus probability of F. We learned that already. The two probabilities have to add up to 1.
Point is 0.21 equals 0.79.
1 minus 0.21 is 0.79. So that's the answer for part B. Part C is probability of E union F. E union F. That would be probability of E plus probability of F. The intersection is empty, so we will not have the third part. The probability of E intersection is empty. So this is our formula. And that would be 0.13 plus 0.21, which is 34. Okay, part D is E intersection F complement, E intersection F complement. So everything outside of the intersection. Well, the intersection is empty. So everything outside of intersection is universal set. So therefore, the answer for probability of E intersection F complement is 1, probability of the universal set. Part E is E intersection F complement. The part of E that's outside of F, that's what that means, which is all of E. So therefore, the answer is 0.21, probability of E. Part F says.
Wait, I'm sorry. Letter D is 0.21 or 0.13?
Letter D is 1.
I said letter E.
Letter E is probability of E. I'm sorry, yeah.
Isn't it 0.13, right?
Yeah, 0.13. Sorry about that. The E, part E is E intersection F complement. That's same as E because there's nothing shared by E and F. So everything outside of F is, E is inside, outside of F. So E intersection F complement is same as E, therefore probability of that is same as probability of E, which is 0.13. Question?
Oh, no, I was on mute.
Okay. Next question says E complement intersection F complement. I have to
Wouldn't
apply.
that be 0.34 minus universal set? Minus 1.
Okay, just tell me what this is equal to.
0.66.
No, we need the probability, but let's figure out this set. E complement intersection F complement is same as?
E union F complement.
E union F complement. So the probability of this is same as probability of this, which is everything outside of the union. What do we have outside the union? We only added up we only found probability of E union F as 0.34. So 1 minus 0.34 is the outside. So .66. Okay. Then E complement union F complement. Last question. How do we find it?
It's the same as probability of E intersection F complement, and it will be 1.
Right. Very good. So probability of E complement union F complement by applying the De Morgan's law, it's equal to probability of E intersection F complement. We already found that to be 1 because E intersection F is empty. So universal set is what outside intersection is. So when they're mutually exclusive, you know, all these additional thinking you have to do. So that's why I brought up that problem. So, okay, so we don't need this 20. We already did problems similar to that. Okay, so we are out of time, so I need to stop here. Only thing is we haven't done the application. Application means the problems are going to be now described in words and you have to identify them as events and things like that. So I just have to, I have the assignment already set. I just have to delete these application problems and then you'll be set. So I'm going to do that right now. You're all set. We will continue this worksheet 9, and also we will start worksheet 10 in the next class.